Hello, gentle mathematicians. Saturday, 25th of November. I thought we might just get started on problem 8. I still haven't been able to finish problem 7. I thought I'd solved it, then I discovered I was missing a point, but I wrote that in the comment. And I haven't been able to solve the last part. I believe we could start on A, B, and D today. This one seems a little more involved. We need to find Q when we have Z equals to 1/2, and that's of course minus Q. Yeah, we have had that before. So that should be trivial. So capital Z of psi plus 1/2. That's the sum of Q to n squared plus minus Q to n squared. So we only sum over the even integers. We should do that out to the left, then I'll be able to do it in one line, I think. Let's do it here. And then we write n as 2m. That's Q to 4m squared. And Q to 4th, that's Q of 4z, so this is equal to capital phi of 4z. Wasn't that what we should prove? Oh, I forgot the 2. There we go. Well, this was A. Now for B. Well, that's actually the same trick. We only get the even guys. We'll just write it up. No, the odd, I think. Yeah. 2 of z plus 1/2 minus 2 of z, 1 minus 24, psi 1 of n, and that's minus Q to nth, minus Q to nth. So unity cancels, and then we get 48 times this when n is, now let's see, if n is even it cancels, so it's only if n is odd. And wasn't that what we should prove? Yeah, of course n positive, because in E2 it's we're summing from unity to infinity, so we are starting with 1, 3, 5, etc. Well, that was B. And D. Now what's that? I thought, if this was plus, then this should be minus. So it's actually minus the result we have up here. Yeah, all right, so let's do the left-hand side. Let's just forget about unity, because 1 plus 2 minus 3 vanishes. So it's minus 24. 3 times 24, that's 72. And 2z that's q squared, and it's minus 3, so it becomes plus, and then minus 48. That's q to 4n. This is a surprise. So the sum of the divisors giving different powers, we have to compare the powers of distinct the sum of the divisors of distinct ends. Well, let's write up the equation we get. Where we put minus 24 outside, and then q to all the odd ones come from here. So let's divide up until odd, n odd. And then when n is even, but not a power of but not a multiplum of 4, we get 3 minus 1 . 2 divides n, 4 fails. And finally, when it's 4, oops, did I do that right? I don't think I did that right. I'll just have to rethink it. From here we get 3 of n halves, and from here we get minus 3 3 sigma 1 of n halves minus sigma 1 of n. And the last guy here, that's when four divides n, and we take powers to q to nth. Oh, let's just take a plus sign. So from here we get sigma 1 of n, like up here. And from this one we get plus 3 sigma 1 of n halves and from here we get minus 2 sigma 1 of n fourth q to nth. And this number 2 shouldn't be there. I didn't expect this complication. So we need to compare the divisors of the sum of divisors of n and n half. Of course, all the divisors of n half are also divisors of n. So which divisors of which divisors of n do we not get? I need to make an example just to check that. So let's say n equals 14. We have the divisors 1, 2, 7, 14. Maybe that was a bad number. And then n half equals 7. And that gives 1 and 7. So it seems the divisors we are missing here are the double of these. Yeah, of course. So this consists of the divisors of n half plus the double of them. Now this cancels. All right. Now this becomes a little more intricate. And I'll try to make a formal proof as well. So we have the divisors of numbers divided by 4. And if we take the divisors of n divided by 4, then they give rise to A1, 2A1, A2, 2A2, AN, and 2AN. Oops, yeah, that's divisors of n fourth. And then n, there we have the original ones, and 2A1 and 4A1. A1, 2AN, 2AN, and 4AN. And that's the sum of all those. So we get NA, A1 here, and 3A1 here, and minus 2 here. That appears, it appears to me that I got the signs wrong. Minus, plus, minus. So my problem here was that I put minus 24 outside the sum. So it's plus here, minus here. And plus here. And that means the number of A1s cancel. Now, 2 A1s here we have 4A1 and 2A1, that's 6A1. Here we have minus 6A1. And the A1 here, that's already, yeah, we should take them all in. So sigma 1 of n, that gives 7 A1s. This one gives 3, so that's minus 9 A1s. And then this one gives 2, so that cancels as well. So we have done this one, and this one. And that's what I wanted to do today. I can feel now my fingers are cold. So we've had a spot of low temperatures here in November, near freezing. Though my flat was a little too cold when I returned home today. Hello, a Sunday afternoon, sharp sun, but still frost. And time to start on part C. It just occurred to me while reading it that D seems to be a specialization of C to P equals 2. And then applying this as well, B as well. But now let's do C in its own right. So I copy the left side. This constant we'll just call alpha, or A. There's no need to use Greek letters. It's obvious that the constant term vanishes, so we'll just take, and it's all k minus 1, so we'll just neglect that as well. We will be using it later, I think, but neglect it for the time being. n q to n, and then plus 1 plus p to k minus 1 a minus a p to k minus first sigma. Now what am I doing here? I feel I've done something wrong here. Here we are summing over sigma of n and then q to n, so right. So we must split in 3 cases. One, just as we did with 2, one where p but not p squared divides n, and then one where p squared divides n. And here we substitute we split up where p fails to divide n. That's strange. I thought I would be able to generalize this thinking here without any problems. I'll just need to take out the 2 different on the same page, on the same line. There we go. And then plus this guy. And here we have a priori that p divides this guy. And we separate the cases where p squared divide n. And then instead of summing over n, we sum over np. That's the new n. So it's sigma n divided by p, q to nth. And the last one, minus a p to k minus 1, summing only over n divisible by p squared. There we go. This seems to be what we should end with. So let's just copy that first. And then the rest might vanish. Now, what do we do? Well, in here it was 1 plus p to k minus 1, and they cancel, I think. There, so there's only a left, and here p squared a times 1 I need to be very thorough here. Let's have a case where p divides n, and then the number of divisors of n divided by p. That sum, oh, it's k minus 1. We get those, and then sigma k minus 1 of n, that contains those to k minus 1 plus the 1 times p raised to k minus 1. So that means that this equals 1 plus p to k minus 1. And of course, or that's not of course, substituting n by n divided by p, of course, in case p divides n. There we go. It's funny, because if I'd prepared this, it would be elementary. And yet I'm quite confused. What I'll do is I'll make a break, make coffee, and then I'll look over it while I drink my first cup of coffee, and then restart recording. Well, the coffee is still brewing. When I came back, I noticed this guy, which of course cancels with this. And that means that we are left with these two. Oh, that should have another color. Which vanish by this formula, meaning we don't need this. Well, that's it. So we are left with the result here, which is what we should get. So when I've had my coffee, I'll continue with part E. I've rewritten the definition of the eta function and then the formula we must prove. And it's just starting in eta of z plus 1/2. Q of, we'll just write it up here, and then 1 divided. Now it becomes minus q to the nth. We have had this before. And this is just q again, and then 2 pi 48th q 120 to the reciprocal of 24. That's strange because that was not what I wrote up there. Oh yeah, it's this is wrong. This should just be this constant. So I mistyped the formula. Yeah. Oh, why was everything red? Silly me. All right. I wonder what we have. Multiplying by eta, then that becomes 1. Yeah, what does that become? Oh. Let us handle the constant term first. So on the left-hand side, we get q to 1/24th. And on the right-hand side, we get, this is q to 12th to the third. That's q to 1/4 divided by q 1/24th and q to 1/6. It's 6/24th minus 1/24th minus 4/24th, and that equals exactly 1/24th. So they agree. So it's just the power series itself that we need to reconcile. So we'll just disregard the constants from now on, and the powers of q, just take into account the infinite product. And underneath, or should we multiply by that on the other side? I would like to cancel something or reduce something. This could be written like q plus 1 plus q2 nth so that could take one of them. But I'm basically missing an idea to handle this minus q to nth. Well, time for another break. Well, back to work. I did get an idea though, and that was to split this into odd and real n, odd and even n. And then this is q plus 1 plus q to 2nth times 1 minus, so each one of them. On the other side, we have if n is odd, then it's 1 plus. And if n is even, then it's 1 minus q to nth. And this can be written, of course. Oh, let's so we need to show that they are equal. So I'll make that a green guy, because that's what we hope to show. And and these two multiplied, that's the odd and the even powers, so we multiply it with them on both sides. And these are only the even ones, so we can just say 1 minus q to 2nth. And that means that this guy cancels with the power here. And now what did I do up there? I'll just correct that. There we go. that's easy. We just multiply on both sides with this. Oh, we can divide up there. So it's just 1 plus q to the nth. So they agree. So it was just a question of keeping your head cold and your feet warm, as the saying goes.